We're going to start our discussion about functions by looking at how functions are represented. And there are four ways in which functions are represented. One is a verbal description. They can be represented using a table of values, a graph, or a mathematical expression. A verbal description might look like $1 for the first minute and 50 cents for each additional minute. Or for a cell phone plan, you might have a base rate for the first 500 minutes and then a per minute cost for every additional minute after that. For a table of values, one thing that comes to mind is income taxes in America. If you pay United States income tax, then your tax is based on formulas determined by the IRS. And in 2021, the tax table indicates if you made, say, $33,000, then you would look here at this line, $33,000, well, between $33,000 and $33,050. And if you're single, you're going to pay $3,764 in taxes. This is just using a table of values. It's a function. For any particular income that you have, you're only going to pay one amount for each filing status. The other two ways to represent a function using a graph and a mathematical expression are things that we are going to explore throughout this course. And so we'll just let that happen naturally. And in fact, we're going to jump to a mathematical expression right now. Here is an exercise. We're going to find the domain of a function that's given using an algebraic expression here. F of x is equal to the square root of 5 minus x plus the square root of x plus 3. The domain of a function is the set of allowable input values. And in the case of this function, we have to consider the values that we're allowed to put into the square root of 5 minus x. And then separately, we're going to consider the allowable values into the square root of x plus 3, keeping in mind this is going to be a real valued function. We only want real numbers here. I think a visual would be helpful for this particular function here. And so I just have a number line here labeled x. I'll just identify a 0 for orientation purposes. And when we consider what can go into the square root of 5 minus x, clearly x has to be less than or equal to 5. So I'm going to mark on my number line 5 and highlight the values to the left of 5. When we consider the square root of x plus 3, we're looking at values that of x that are greater than or equal to negative 3. And so on our number line here, I'm going to give a negative 3, and we're going to consider values that are larger than negative 3. Now, in order for me to put a number into this function, I've got to satisfy both of these simultaneously, which means we're looking at the region of overlap here. And so the domain is the closed set from negative 3 to 5. Let's look at one more, same instructions. And our function is g of u is equal to u plus 1 over the quantity 1 plus 1 over u plus 1. This is a complex fraction, which is how we refer to a fraction that itself contains a fraction. And right away, when we're considering the set of allowable input values, I want to look at what will make any denominator equal to 0. And here, with this 1 over u plus 1, I see that right away I can say that u cannot be negative 1. Now to continue considering this fraction here, we're going to simplify the complex fraction, which means I'm going to multiply numerator and denominator by the denominator of any of the smaller fractions that I see here. In this case, that means I'm going to multiply numerator and denominator of the big fraction by u plus 1. When I do that, I have u plus 1 quantity squared in the numerator, and in the denominator, I need to distribute the u plus 1. I end up with 1 times u plus 1 as my first term, plus 1 and the u plus 1's divide out, or cancel out. This is going to give me u plus 1, the quantity squared, over u plus 2. Now, looking at this denominator, I can see that u cannot be negative 2. And as a quick mental check here, you can see that if you were to put negative 2 in place of u in the original expression, then I would have 1 over negative 2 plus 1. So that would be a negative 1 I'd have 1 minus 1. That would give me 0 for the denominator. But this was just maybe a quicker way to do that. In any case, the domain is the set of u such that u does not equal -1 or -2. You know, I'm going to put those in numerical order. The set of u such that u does not equal -2 or -1. I could have left it as -1, -2. Mathematically, it doesn't matter. That is just a personal thing that I had there. Just for a reminder of some math terminology here. In the first example, we wrote the domain down using interval notation. That's a valid way to represent a set of numbers. Well, a continuous set of numbers. In the second example, I used what we call set builder notation. The curly braces indicate the set of, and then we wrote the variable under consideration u, right? If this was like an f of x here, I would have put x here. The vertical line is such that. And so these mathematical symbols in English are the set of u such that u does not equal -2 or -1. We could have done this in interval notation, and I'm just going to give you a number line so that you can see what the interval notation would have meant in this case. -2 here, -1 here, and the domain would be everything not including -2 or -1. And a lot of people in this situation would say -infinity, -2, and then they would put the little union symbol, and then -1 to infinity, which is almost correct, but it's leaving out the part between -2 and -1. So to fix that, what I would need to do is actually add another interval in between. And so it would look like the interval from -infinity to -2 together with, or union, I made a better union symbol there, -2 to -1, union -1 to infinity. And once I'm going to write down this many intervals, set notation just is more appealing to me.